Good afternoon. My name is G. Mahendraswaroop. I am from CSM department. Subject is distributed system and topic is logical time and logical clock. So logical time and logical clock was developed by Lamport in 1978. So logical time and logical clock was designed by Lamport 1978. So here in this we are having two types. Instead of synchronizing clocks, event ordering can be used. So here if two events occur at the same process, pi of I is equal to 1 to 3 so on n, then they occur in order to observed by pi. So here it is observed by the pi, that is the order is ith. So here order is I. So here if two events occur at the same time, here the process will be do process in the form of pi, where I is equal to 1 to 3 so on n, and they occurred ordered observed by the order I. So here order is observed by the order I, and when the message m is sent between two, here the messages are sent between the two processes. So here the process is m. So here the message means m will observe it as m, or will say it as m. So here the m process is done between the two events. So first one is send m happened before the receiving m. Here the sent m is having happened before the receiving m. So here the instead of synchronization clocks, the events order can be used in the two events occurred at the same time. Here two events are occurred at the same time of the process pi, where I is equal to 1 to 3 so on n. So they occurred in order in the form of pi, where the order is I. Here order is represented by the I, and the process is represented by the pi. So here when the message is represented by m. When a message m is sent between the two processes, means here sending m happened before the receiving m, means sending m send the request message, and receiving the send the response message, means here respond happened after the sending m, means request sending after the request sending after only receiving will be happen. That is the meaning. Next one, happened before relation. Previous one is instead of synchronization. Here happened before the relation. Here obtained by the generalization the above two relations. So here they are they obtained in the obtained by the generalization in the form of two relations. So here it is denoted by arrow. So here the relation is denoted by arrow, like this arrow. So HB1 comma HB2 are of formally statements. So here HB1 HB2 are formally statements of the above two relations. So here we are having two relations. The relation is represented as the arrow button, and here we are having two statements, that is HB1 and HB2, and the other third one is HB3, means here it is happening before the transitive, means here before the transitive HB3 is happened. So here we are giving the note as not all events are related by example A turns to E and E turns to A, means A turns to E or E turns to A. So here events will be not related in this form, A turns to E and E turns to A. Considering A and E, so these two are events. Here the different processes, and here there is a different processes, and there is no chain of messages to be related by them. So here A turns to E E tends to A, this like this it won't be happen, and there is a no chain relation of sending the messages, and they are not related by, they are said to be concurrent. So here they are not related by arrow, and they are said to be concurrent, and they will be written in the form of A parallel to E. So they won't. So here there is not relation. There is no. There is not a related by arrow button, and there said to be no concurrent. So here we are considering A and B, and the different processes. Here these two are different processes, and there is no chain messages, and to the relation them, and there is not their relation, like A turns to E, and they are said to be as a concurrent, and they are said to be as a concurrent, and they will be written in the form of A parallel to E, not A turns to E. So here A turns to B means P1, or C turns to D means P2, and B turns to C means M1. Also B turns to F because of M2. So here messages we are taking process 1, process 2, process 3. So we are taking process 1, process 2, process 3, and here A, B, C, D, E, F. These are the processes we are taking, and first A is sending the message to the B, and B is sending the message to the C by the message M1, and C is sending the message to D, and D is sending message to the F by the M2. So here we are taking the physical time, and there is no connection between the E and F. So here E is a separate. So there is a connection between them, that is A turns to B turns to C turns to D turns to F. There is no connection for the E. So here we are sending the messages for we are doing the processes for 3, and in that we are sending the messages by the processing, that is A to B to C to D, and D to F. So here A is sending the message to B, and B is sending the message to C by sending the message with the M1, and C is sending the message to D, and D is sending message to the F with the M2. And next one, Lamport Logical Clock. Here logical clock is monotonically increasing software counter. So here logical clock is monotonically increasing software counter. It need not related to the physical clock. Here the logical clock is not related to the physical clock, and each process is represented with the PI, has a logical clock, that is Li. Here logical clock is represented by Li, which can be used to apply logical timestamp at the events. So here which can be used to apply the logical timestamp to the events. Here logical clock Ci, here Ci is incremented by 1, means here logical clock 1 is incremented with the by 1 before each event at a process Pi, means here Li is incremented by 1 before the each event at a process Pi. And next logical clock 2, here we are having two types, that is A, when process Pi sends the messages M, it piggyback T is equal to A, means here piggyback is represented with T is equal to Li, and where MPJ receives M comma T, it sets to Lj. So Lj is equal to maximum of Lj comma T, and applies to LC1 before the timestamps the event receives M, means here timestamps events receives M. It will happen before the timestamps event receives M. And next, E turns to E dash. Here E turns to E dash implies logical clock E less than or equal to logical clock E dash, but not vice versa. Means here we are saying that E turns to E dash implies logically E less than or equal to logical E, not E dash. It won't be the vice versa. Only it will be the LE less than or equal to LE dash. LE less than or equal to LB, but it is represented in the form of E parallel to the B. For example, here each of the we are having three processes, process 1, process 2, process 3 has its logically clock initialized to 0. Means here we are having three processes and the logical clock is initialized to 0. The clock values are immediately after the event, means event happen. For example, 1 for A, next 2 for B, like that it will be happen. For M1, 2 is a piggyback and C gets a maximum of 0 comma 2 plus 1 is equal to 3. Means we are taking that maximum of 0 comma 2 plus 1 is equal to 3. Like this we are taking, and we are representing in the form of diagram. Here process 1, process 2, process 3, and we are having the processing events, that is A, B, C, D, D, F and E. But we are not having the connectivity with E. Only we are having the connectivity with A to B, B to C. Means here B and C are sending the messages with the M1, and C, D and D to F. Here D and F are connecting with the message, that is M2. Here there is a physical clock. Next one, vector clock. Here it is they are designed by the Mlritm 1989 and Fitch 1991. So here vector clock was designed by the two persons. First person is Mlritm 1989 and Fitch 1991. Here vector clocks overcomes the shortcoming of Lamport logical clock. So here there is a drawback for the logical clock. To overcome this logical clock, we are introducing the vector clock. So here vector clock overcomes the shortcoming of Lamport logical clock. Here it is represented by L of E less than or equal to L of E dash. So does not implies the E happens before E dash. So here E won't happen before the E dash. And the vector clock Vi at a process Pi is an array of n integers. So here vector clock Vi. So vector clock is represented by Vi at the processor Pi is an array of n integers of vector. Each process keep its own vector clock, that is Vi. So here each every process keeps its own vector clock, that is Vi, used to timestamp local event. So here we are using the timestamp as a local event, that is represented with Vi of I is a number of events that PA has timestamped. So here V1 of Vi of I is the number of events. So this is the number of events that PA has timestamped. Next one, this is one. Next one is Vi of J. But J is not equal to I. So here J is not equal to I is the number of events at a process Pj that Pa has been affected by J. So here Vi of J Here j is not related to I. So is the number of events at the pj, and that here pi has affected by pj. That's why j is not equal to I. But I is equal to j will be happen. But j is not equal to I won't happen because pi is affected by the pj. That's why j is not equal to I. Next one, logically clock, Matrin 1989 and the French 1991. Here we are having some rules to update the clock. In vector clock, we are having some rules to update the clock. That is VCI. VC1 means vector clock. Vector clock 1. Here it is initialized by Vi of j is equal to 0 for I comma j, where I comma j is equal to 1 to 3 so on and so here in the vector clock, to update the clock we are having the some rules. In that, first rule is vector clock 1. Here it is initialized Vi of j is equal to 0 where I comma j is equal to 1 to 3 so on and next point is vector clock 2. Before process pi, the timestamp an event, it sets Vi of I is equal to Vi of I equal to Vi of I plus 1. So here before p process pi, timestamp and event, it sets to Vi of I is equal to Vi of I plus 1. Like this it will be represent. Next rule, vector clock 3. Here pi piggyback t is equal to Vi on every event it sends. Means here pi piggyback t is equal to Vi on an every event sends a message. Next, vector clock 4. When process pi receives m comma t, it sets to Vi of I. So here when processes pi receives m comma t, it sets to Vi of j is equal to max of Vi of j comma tj. Means Vi of j is equal to max Vi of j comma t of j, where j is equal to 1 2 3 so on and like this will represent. Here before the next event adds I to own element using the vector 2. So here before the event adds I to its own elements using the vector clock 2. Means here we are using the merge operation. For example, P2 of 0, 0, 0 turns to 0, 1, 0 and turns to 0 to 0 and next 0, 3, 0 so on 1, 4, 3. So here sending and receiving. So here processes all are initializing with the 0 and after that next process 0, 1 sending the message, 0 and next one process 2 sending the message and next process 3 sending the message. After that totally we are receiving 1, 4, 3. Now receiving the message from process P3, that piggyback t is equal to 1, 4, 3. We'll see in the diagram. Means here like this you are sending the message. Means here process P2 0, 0 turns to 0, 1, 0 means message sending 0 comma 2 comma 0. Next third one 0 comma 3 comma 0. So totally we are getting the piggyback by in the form of t is equal to 1 comma 0 comma 3. Like this we are receiving the message. Next here meaning of equal to, less than or equal to, less than for vector timestamp comparison of elements. Here v is equal to v dash means v of j is equal to v dash of j, where j is equal to 1 2 3 so on. And next v of existing v dash, here v of j existing v dash of j for j is equal to 1 2 3 so on. And here v is less than or less than vj means here v existing v dash and v1 of v dash. For example v1 and v2, here sending and receiving the messages 1 comma 3 comma 2 and 1 comma 3 comma 3 means from here to here 1 is incremented, so 1 comma 3 comma 2 plus 1 1 comma 3 comma 3 1 comma 3 comma 2 and here 1 comma 3 comma 0 1 comma 3 comma 2 1 comma 3 comma 2 1 comma 3 comma 2 and 2 comma 3 comma 1. Like this comparison vector timestamp. And here we are taking the example vector clock example, that is p1 a 1 comma 0 comma 0 and b 2 comma 0 comma 0 and piggyback 2 comma 0 comma 0 on message m1. And next process 2 on receipt of m1 getting the maximum of 0 comma 0 comma 0 and 2 comma 0 comma 0 equal to 2 comma 0 comma 0, and we are adding the 1 to the process p2 means after adding the process p2 we are getting an element by 2 comma 1 comma 0. Note e turns to e dash implies vector of e less than vector of e dash, then it converts as true means here e turns to e dash implies v vector of e less than vector of e dash converts true assignment. Next va less than or equal less than of v of f can use the parallel event. For this means v of a less than v of f will use it for parallel event means like this c parallel to e, not in the form of like this, we'll write like this c parallel to e because neither v of c less than or equal to v of e nor v of e less than or equal to v of c. So like this we'll represent, not like this. So here we are representing the message in the form of diagram. Example process 1, process 2, process 3. So here a b c d d f and e. So here process p1 of a 1 comma 0 comma 0 and process 1 b 2 comma 0 0, and next in the process 2 message is sending between the two from process 1 to process 2 in the form of b to c by using the m1. Here in the process from process p1 where b is sending the message to c by adding the 1, that is from here 2 comma 0 comma 0. So we are adding the 1 by using the sending the message. After sending the message by adding 1 we will get in the form of 2 comma 1 comma 0. Next in the process p2 again by adding the 1 we are getting 2 comma 2 comma 0. After that In process P3, the message is sending from the process P to process P3 by using M2. Here we are incrementing the 2. Here we'll get, after incrementing the 2, we are getting 2 comma 2 comma 2. Like this we are getting. So here vector 1 example, here process P1 A comma 1 comma 0 comma 0 and B of 2 comma 0 comma 0 and piggyback means 2 comma 0 comma 0 by sending the message M1 and P2 receipt by using the M1, here getting as 2 comma 1 comma 0 means here adding 1 means incrementing the 1. After that again from C to D 2 comma 2 comma 0 and from D to F sending the message with the M2 and here we are adding the 2. After adding the 2 we are getting 2 comma 2 comma 2. And second example, here initial vector example 2, here process 1 we are taking, previously we have taken 3 matrix. Now we are taking the second example, we are taking the 4 matrices. Process 1 is equal to 0 comma 0 comma 0 comma 0 and process 2 is equal to 0 comma 0 comma 0. Process 3 is equal to 0 comma 0 comma 0 and same as process 4 0 comma 0 comma 0. So here events and result vector. So first one p at the rate p1 local means the result vector p1 is equal to 4 zeros. Second one sending the message from process 1 to process 2, sending the message with the m1 and here p1 is equal to 2 comma 0 comma 0 comma 0 and message receives with the 2 comma 0 comma 0 comma 0. And next third one p1 at the rate p2, here m1 is receiving with the matrix 0 comma 0 comma 0 comma 0 comma 2 comma 0 comma 0 by incrementing the 1. So for this 2 comma 0 comma 0 comma 0 we are incrementing with the 1. So that is in the second place. So after incrementing we are getting is 2 comma 1 comma 0 comma 0. Like this we are getting. Next fourth one b at the rate p3 local means p3 is equal to 0 comma 0 comma 1 comma 0. So here fifth one m2, here process p3 is sending to the process p4 with the form of p3 is equal to 0 comma 0 comma 2 comma 0 and the message receiving in the form of 0 comma 0 comma 2 comma 0. Sixth one r2 at the rate p4 of m2 receiving, here maximum of 4 zeros. Next 0 comma 0 comma 2 comma 0, for this incrementing with the 1. So after incrementing 1 we are getting process p4 with that 0 comma 0 comma 2 comma 1. Next seventh one c at the rate p2, it is a local means we are getting as p2 2 comma 2 comma 0 comma 0 and m3 means here sending the message through m3. So p3 is equal to 2 comma 3 comma 0 comma 0 and message receiving in the form of 2 comma 3 comma 0 comma 0. Next ninth one r3 at the rate p3 of m3 receives means by using m3 it receives maximum of 0 comma 0 comma 2 comma 0 and 2 comma 3 comma 0 comma 0 means here we are incrementing with the 2. After incrementing with 1 for 2 we are getting it as means here we are taking this 2 comma 3 comma 2 comma 0 and we are doing the plus 1. After that we are getting it as 2 comma 3 comma 3 comma 0. And next one 10th point d at the rate p4 local means here we are taking the process p4 as 0 comma 0 comma 2 comma 2. Next, sending the message from P4 to P1 with the form of M4 means P4 0 comma 0 comma 2 comma 3 and receiving the message in the form of 0 comma 0 comma 2 comma 3. And last one, R4 at the rate P1 of M4 means here process P1 receives M4. By incrementing the 1, we are getting as P2 2 comma 0 comma 2 comma 3. After incrementing 3 comma 0 comma 2 comma 3. Like this we will get. And the final vector totally for this example, final vector P1 is equal to 3 comma 0 comma 2 comma 3. This is the final vector for process 1 and process through 2 comma 3 comma 0 comma 0. And final for P3 2 comma 3 comma 3 and P4 0 comma 0 comma 2 comma 3. This is the final vector. Next example, here we are first fixing the event E means here E turns to X if V of E less than V of X means here 3 process we are taking and the 3 matrices. First we are sending the message with the 3 zeros and after that in the second process it is adding 0 comma 1 comma 0 0 comma 0 comma 1 and here from process P1 it is sending the message to process P through that is 2 comma 0 comma 0 means here incrementing is happening 2 to 0 and next again it is sending the message from process P2 to process P through P2 by adding the 2 means 240 incrementing 2. After incrementing 2 we are getting 2 comma 4 comma 2. Next and from process P2 we are sending the message to process P1 that is 230 to 550. Next one again we are sending from process P2 to P1 with 250 to 450 and again we are sending the process P2 to process P3 with X that is 262. By incrementing 4 we are receiving 264 and next process P3 is sending the message to process P2 that is 243 to 273 here receiving. Next one, detecting the global properties. Here we are having the properties 3 that is garbage collection, deadlock and termination. Garbage collection, here we are having the 2 objects process 1 and process 2. In that we are taking the reference 2 objects and in process P2 also we are taking the garbage 2 objects. So here from process P1 we are sending the message to process P2 and process P2 is receiving responding the message to process P1. Deadlock, here process P2 is the process P1 is sending to the process P2 but here it is waiting condition and process P2 is sending to process P1 here also waiting condition, that's why it is a deadlock. And termination, process P1 and process P2 here passive and active, we are sending the message from process P2 to process P1 by using the activation. Means here garbage collection, here object is considered to be garbage if they are no longer any reference, means if there is no reference to it anywhere in the distributed system, the memory takes up object can be reclaimed once it is known to be the garbage. Means if there is no garbage, if there is no reference, then it is reclaiming to it to get the garbage. To check that the object is garbage, we must verify that there is no reference to it anywhere in the system to get to check whether it is having the object is having the garbage or not, in the form of no reference to anywhere in the system. If it is having no reference in any system, then it is not having the garbage objective. Next here, process P1 has two objects that both having the reference. One has the reference with P1 itself, and second one is having the P2 reference to it others. Like this, process 1, process 2. It is having the reference and it is having the reference. And process P2 has one garbage object with the no reference to it anywhere in the system. Then it has an object for which neither P1 nor P2 has no reference, but it refers it to the message that is it transits between the two processes. Means here it is in between the transit in between the two processes. Next, that is a garbage. Next one, deadlock detection. Here a distributed deadlock occurs when each of the collection of process waits for another process to sending its a message, and where there is a cycle in a graph of its wait for the relationship. So here deadlock occurs means when process P1 and process P2 here sending the message, means here waiting happens, and process P2 is sending the message to process P1, here also waiting happens. So that's why we are saying it as a deadlock. Next one, so that process P1 and process P2 are each waiting for the message from the other, so the system will never make a process. So that's why we are saying it as deadlock. Thank you.